Okay, section 4.2, open loop control and the step response. This is a section from the Real-Time Computing for Mechanical Engineers book that I wrote with Garbini and Devine. I'm Dr. Picone. MIT Press website has more info about the book, and the rtcbook.org companion website is very helpful for lots of resources about the book. So, open loop control and the step response. In this chapter, we use open loop control, which depends entirely on predictions about what will happen if a certain input is applied to the system. Measurements of actual system responses can inform these predictions, but not in real time. We're not using that measurement information in real time to adjust any inputs in open loop control. Our open loop controller will take a user's commanded angular velocity of the motor and must decide the voltage Vs or current Is to be applied to the motor. One approach to designing an open loop controller is to choose a step input voltage or current that responds to the desired steady state angular velocity in model predictions. With a voltage source, we have the following step response. For the voltage source electromechanical system, the step input is, so Vs is m times the unit step, where m is a real constant and Us is the unit step function. The step response can be found from either the state space or the transfer function model. The state space model yields the scalar solution because we have a single output here, single input and a single output. So we have x of 0 being the initial condition of the state variables. So in our case, it's the initial current in the inductor and the initial angular velocity of the load. We also have e to the at, which appears in this expression a couple times, is the matrix exponential. For our motor model, with the initial angular velocity and armature current 0, this simplifies to this expression for 2. The output, y of t equals omega j, so equation 2 is the angular velocity response. If the system is stable, i.e. if all eigenvalues of A have negative real parts, there is a steady state angular velocity given here. So this is the steady state angular velocity given a step input in the voltage source. Okay, so returning to open loop control, the question of the proper voltage to apply has been reduced to the question of what M should be in order to yield the desired steady state angular velocity. Solving equation 3, we get M equals this expression, where we have used the fact that C A inverse B is a scalar. Okay, so we divided both sides by this matrix multiplication, C A inverse B, which if it was a matrix wouldn't work, but does work because it turns out to be a scalar. Equation 4 gives the value of a constant voltage to be applied to the motor to yield a steady state angular velocity omega j infinity. Substituting the state space matrices from section 4.1.1 into equation 3, the steady state step response is given here. So in terms of system parameters, with the motor constant Km, the damping coefficient B, and R being the resistance of the armature. The motor constant Km is typically much larger than the damping coefficient B times the armature resistance R, so the approximation omega j infinity is equal to M divided by Km can be useful. Okay, it's a very simple expression for the steady state angular velocity. With the state space matrices from section 4.1.1, equation 4 becomes this, simplifying with the same assumption, Km squared is much larger than B times R. We get this expression, Km times omega j infinity. So we can choose our voltage input based on a desired output angular velocity and the known motor constant. And this is actually a pretty good model. We often don't know B very well, but we've seen that the result here doesn't depend very much on B. So in order to get some angular velocity in steady state, we can multiply that angular velocity by the motor constant to get approximately what steady state voltage we should be applying. With a current source, things are a little different. So with a current source step input, N is the scaling value times the unit step. So N amps of current being applied to the motor. The step response derivation of section 4.2.1 through equation 4 applies here. Replacing M with N, we get the steady state angular velocity N relationship as B omega j equals Km times N. This makes sense. Negative B omega j is the damping torque, and Km times N is the motor torque. So these are equal in magnitude and opposite in direction when the system is in steady state. That is, when the inertial element is not accelerating, the two applied torques must sum to 0. So to drive with a current source, a constant velocity omega j, apply N US with N being equal to omega j times B over Km. It is worth noting that the parameter B, the damping coefficient, is the most difficult to measure accurately. So a prediction for the steady state current may be less accurate than for steady state voltage. This is much more sensitive to the value of B than our previous solution was for the voltage source case. In our target system, the damping is very small, so little current is needed to maintain a constant velocity. So all that is to say that when we have an amplifier driving our motor that is well approximated by a voltage source, it is relatively easy to determine which voltage needs to be applied to get a specific angular velocity output. On the other hand, when we have a motor amplifier that is well approximated by a current source, as we do in the T1A system, it is not so easy to predict a constant current that's going to give us a constant angular velocity that we would like to specify. And this is because the parameter B matters a lot more in the current source prediction. So that is a little introduction to doing open loop control for a DC motor. In the end, we're going to want to measure what that actual angular velocity is or position is and feed it back. But for this chapter, we're going to be satisfied with just applying a constant voltage, or actually a constant current in the case of our amplifier, and seeing the constant angular velocity that results. Okay, I'll see you next time.